Hey everybody, welcome to part 2 of my AP Calculus Unit 2 review, okay? Part 1, I made a video about that. That was covering, basically the introduction to differentiation. This is a continuation of that video, but we're going to be talking about differentiability and continuity, and then later in the video we're going to talk about the derivative rules that you should be familiar with for the exam. Okay, so the reason why it took so long is because I really wanted to make sure you guys understand the concept of what a derivative is and how to find one, okay? We're going to leave those formulas off to the side for now because I want to show you, like, when can you actually use those formulas. And then later in this video we're going to talk about some examples where you actually do use those formulas. And really some shortcuts actually, but yeah, let's get started. So first, we're going to talk about the criteria for differentiability. Okay, so we're saying the criteria for the function f to be differentiable at x equals a. Differentiable just means, are you able to take the derivative of your function f? Okay, so are you able to find f prime of x? Okay, so, well, what are the criteria? So the first one I'm going to put is the second one, and that's pretty easy. Your slope has to be defined. I guess I should put slope must be defined. So yeah, let me actually do that. So your slope must be defined, and that should be pretty straightforward for you. If the derivative is the slope, and you want the derivative to be defined, then you have to have your slope to be defined as well. So your slope must be defined. And what this does is it rules out things like if your slope was 1 over 0. This is undefined. This is the opposite of this. This is undefined, so you're not going to have a slope. So, well, what happens if you're, like, what does that look like? So, I'm not going to draw the xy axis, I'm just going to draw it. So, if you have, like, a function here, up 1 over 0 just means it's a vertical line. So maybe your function looks like this, it goes off that way, and then it goes off this way, right? And you have a vertical line here. Your slope is not defined here. So you cannot find the derivative right there. You can find the derivative everywhere else, because it doesn't show anywhere else that it's going to be undefined, but just not at this particular point. Because, you can't have, you just can't have that, basically. Okay, so that's the easiest one out of the way. The first one actually connects differentiability with continuity, okay? And it basically states that, actually, I'm going to hold off on telling you what it is. I'm going to build us up to there, okay? So let's think about this. We have a function and we want to take its derivative. So we want to find a slope. So let's say we have our function and we can just, make it something like, we just go over here and maybe we have a discontinuity here and then we jump down here and boom. So we continue off this way and we continue off that way. Oops, let me make that a little clearer. Okay, so here our function doesn't exist. So how can we find the slope at that point if that point isn't even there to begin with? So, okay, so that our function has to exist. Let's write that down. Hold on, there's more to that, okay? So our point has to exist, right? For that function. Like, the function has to exist at that point. Well, what if the point was there? What if we just kind of filled that one in, and now the point exists? We have f of whatever this is. Well, the thing is, there's an issue, because now you're not, like, it's hard to see, like, okay, well, this derivative, like, the slope is going to be kind of like here. Oops, your derivative looks like more of a horizontal line right there, but, like, up here it's a little different, because, like, this is weird. Like, this gives us a weird situation. So if we're not continuous, if our function doesn't continue, then we can't be differentiable. And let me show you a little more of that. Because remember, our limit definition of a derivative was lim as h bar to 0 of f of x plus h minus f of x over h. Okay, so to find a derivative, we have to have this limit, right? We have to solve this. But if the limit doesn't exist, then we can't solve it, so we can't find the derivative. So we need the limit to actually exist. And that means that the limit from the left and from the right have to be equal, because that's what it means for a limit to actually exist. The left and the right hand limits must be equal. So that tells us, so here, if from the left and the right, we from the left we have here, and from the right we have there, we can't actually find our limit, so our derivative doesn't actually exist. So that's interesting. So does that rule out everything for continuity? Well, that rules out two of them. The other one is that the actual function must be equal to the limit. And again, if the function and the limit don't agree, then this is going to be weird, and we don't actually have a point. Because let's say we had a removable discontinuity. So let me remove this out of here. So again, here we can't find the derivative. We already established that because the point doesn't exist. What if the point existed down here? Well, the limit is up here, so if we evaluate this limit, we're going to get up here. But the point is down here, so we're finding the derivative here, but we're finding the derivative at one point, and that doesn't work. So that rules out everything for continuity. So f must be continuous at x equals a. So continuous at that same x value, at x equals a. Okay, so this is really, really strong though, because we're saying f must be continuous in order for f to be differentiable at that point. So continuity, so let me write this down here. Continuity, actually, I'm sorry, let me write it the other way around. Differentiability implies continuity. So, because if you're differentiable, that tells you that you meet these three requirements, which the third one we don't have yet, but we meet these requirements, and one of these requirements is that you're continuous. So if you're differentiable, you have to be continuous. That's part of the definition. So we can actually write this as shorthand. We can say D implies C. And some of you might be tempted to write like the arrow back that way, but continuity doesn't imply that you're differentiable. I'll show you an example later where the function is continuous, but it's not differentiable. You cannot find the derivative at a point, and that's going to lend us to the third reason, okay? But if you're not continuous, then you cannot be differentiable, because look, if you don't meet this criteria, if you don't meet the first criterion that, f is not continuous, let's say, then, you have to have these three for f to be differentiable, and if you don't have at least one of them, then f cannot be differentiable. So if you're not continuous at x equals a, you're not differentiable at x equals a. So that's another really, really important consideration to make. So differentiability implies continuity, and not continuity implies not differentiability. So that's what we call the contrapositive, if you're familiar with some proofs and stuff. If you're not, don't worry, you don't need that. Okay, so what's a case where you actually have like continuity but not differentiability? Well, let me show you. What if, let me do it down here. Let's make sure it's nice and bold here. If you are, let me put it down here. Let me just do this, and let me just put the x-axis down there. Okay, so if you have a function, let's say we go like this, and then we go like that, right? This is interesting, right? We're continuous. I never picked up my pencil. Actually, I think I probably did, but don't worry about it, or my marker, whatever. We're continuous. Like there are no breaks in the graph. But like up here we have like this, what we call cusp. Okay, so let me actually write that. It's a cusp. And basically what that means, it's a pointy edge, right? How can we find the derivative of a pointy edge like that? Like it's like, where are you going to take the derivative? Like this, or like that, or like this, or like how? Well, you can't. You cannot take your derivative. Because, let's say this is our x equals a value, right? So we can say a, right? A little bit to the left of a, you have a very positive slope, but a little bit to the right of a, you have a negative slope. So, even like the tiniest little tiny bit you walk over, you're going to have completely different slopes. So, because it changes that x equals a. Now, if it was smooth, that would be fine. But, so this kind of ties into our idea of limits. It's the limit from the left and from the right, or the limit of the derivative from the left and from the right, they're not the same. So, I mean, it's kind of the same thing with limits. If the limit from the left and right don't agree, then you're not continuous. Here, if the derivative from the left and the right don't agree, you're not differentiable. So we can say that f prime from the left, I'm going to do a little subscript minus sign. That's a notation. You don't have to be completely familiar with that, but it's good to know. It's a good way of shorthand of x must be equal to f prime from the right of x. So a little subscript positive sign, plus sign. Your derivative from the left and the right must be equal to each other. That way, you know, this, you can avoid things like this. And this, you can get rid of. So yeah, that's basically all of differentiability. These are the three criteria for differentiability. And for a function to be differentiable at x equals a, you have to have these three things. And I would definitely suggest remembering them, not memorizing them, just remembering them and making sure they make sense. That's why I'm doing this for you, so that it makes sense to you, okay? Because sometimes I'll ask you, well, state a reason why this is not differentiable, or state a reason why this is not continuous. So if you need a refresh on the criteria for continuity, definitely watch the first video on this series, on the Unit 1, that video. So make sure to know the criteria for continuity, and then these for differentiability. This one's a freebie, the first one, because it's like, oh, it's just continuous, you know, and you just have to remember the three for continuity. Yeah, I mean, that's basically it for differentiability and continuity. Let's now move on to the derivative formulas. Okay, so these are some of the formulas that you need to know. I know there are a lot, and this is about half of them. And yes, there are a lot, but trust me, you'll understand them. It's okay. And you can prove all of these using the limit definition of a derivative. You can try it out. I have videos on them. So I have a video proving this, and I think I might make a newer video, because I made that a long time ago. So I have a video about this, I have a video of this, actually soon of this. Actually, I think I have another old video on this. I have a video on this, and I will have a video on these two, e to the x and ln x, pretty soon. And these I can derive for you right now. So, first, let's just, you know, understand what we're doing. So we're going to take the derivative. And so I kind of want to walk through all these. So a and n, and you can see down here we have a, and again a. They're just constants, okay? If we have, like, for example here, let me just do an example for each of these, actually. So derivative of, 5x squared is going to be, we're gonna take the 5, we're gonna keep it, we're just gonna keep it. We're gonna multiply that by n, which is our exponent. So we're gonna do 5 times 2 times x, right? And then to the n minus 1, which is 2 minus 1, which is to the first. This is just going to give us 10x. Okay, so let's walk through what we just did. The way I like to remember it is you just hop the exponent to the front, multiply by whatever's already there, and then just subtract 1, and that's it. So, you know, I just did that. And I can give you a couple other examples with these three rules. Unless, yeah, well, I'll figure it out. Okay, so, actually, let me skip these three, and let's move on to these, because I think this will give us some intuition for more derivatives here. So, derivative of e to the x is itself. So, let's basically, we can give an example here. Actually, let me do it this way. d dx, right, just the derivative of something. This is our operator, that's what it's called, a derivative operator. Well, what if we have 5e to the x? Well, we're going to keep the 5 here, and we're just going to leave it with 5e to the x. And that's it, that's our answer. Okay, well, how about the derivative of the natural log of x? Okay, well, this would be, I don't know, we could say, we could also do like, yeah, actually, let's do ln of x squared. And there are a couple ways to do this. Once we talk about this one, we'll be able to do it in another way. But remember, with the logarithm rules, you can just hop the exponent to the front, so we can say this is still the derivative of 2 ln x, right? That's just one of the exponent rules, you know. And so the derivative of this is going to be 2 times 1 over x, because that's the derivative of the natural log of x, so 2 times 1 over x. And you can leave it like that, or you could say it's 2 over x. These are both acceptable answers. I'm getting right up to the edge here. Let me do it this way. Yeah, 2 over x. Yeah, so 2 over x. So that's an answer for that. Okay, so now let me show you why these two work, okay? Because I'm writing pretty slanted. I'm sorry about that. So let me actually, yeah, let me erase these. Sorry about that. Okay, basically, a to the x, which is a for any number, you can rewrite it as e to the ln of a to the x. So here, let me show you. So a to the x is equal to e to the natural log of a to the x, and I'll show you why. E to the something and ln of something are inverses of each other. They cancel each other out, so the e and the ln will just cancel out, and you're left with a to the x. Okay, well, why did we do that? Isn't that like redundant? Well, here, look, because what you can do is you can say e to the, you can move this x to the front. We have e to the x times ln of a. Okay, well, we didn't study this derivative. We just know what e to the x. We don't know what e to the x ln a is. So let's look at the product rule. So the product rule, actually, no. Let's talk about the chain rule. This is the chain rule here. This is our new friend. And it basically says that the derivative of a function of another function, so f of g of x, I didn't include the x's here because I didn't want to make it too long, like out here. So f of g of x is equal to f prime of g of x times g prime of x. So what that would look like is, let's say we have, let's say we had 5x to the, hold on. Oh yeah, let's do it this way. So let's say we had the derivative of, I don't know, let's say x plus 2 cubed, right? You could FOIL it out and do all that, but that's going to be pretty messy, if we want to do a bunch of derivatives and stuff. So what we're going to do is we're going to say, well, what's the derivative if we treat x plus 2 as its own like entity? So then we can pretend this is like some other x, right? So we treat it, so we do the same power rule here. This is called the power rule, what we first did up here. So we'll say that this is 3, this is going to be 3 times x plus 2 squared, because we hopped this to the front, subtracted by 1, there was nothing there anyway, so that's it, so 3 times x plus 2 squared. But then we also have to multiply with g prime of x, the derivative of the inside, because g is our inside function. Well, the derivative of x is just 1. Well, actually, hold on. The derivative of a number is 0. You can think of that in 2 ways. You can think about that as like, well, if you're taking d dx of 2, you can think of that as x to the 0 power, right? Because x to the 0 is just 1. So, and this is going to be the derivative. Actually, no, because once you take the derivative, it's going to give you 0 in the front, right? So 2 times 0, x to the negative 1, right? This is what we did. And this whole thing is just going to go to 0. So the derivative of any just constant, just a 2 or a 5 or a 1 million, is just going to be 0. And you can think about that as also another way. If you have a horizontal line, let's say this is y equals 2, that's kind of horizontal, yeah. If this is y equals 2, it has no slope. So, the slope is going to be 0. So, yes, then we're going to multiply this by 1, because, the derivative of x is just 1. We do 1 times x to the 0, which is just 1. And once you do some more practice with the power rule with that, stuff like this, that'll definitely help you. So this, we can actually just remove the 1 and just say this is 3 times x plus 2 squared. We could FOIL it out if we want, but there's no real need for that. Okay, so we use the chain rule, so now let's use the chain rule up here. So we're going to have, well, this is like our inside function, the x times ln a, so we're going to treat it like it's the outside, so we have e to the x ln a multiplied by the derivative of the inside. So this, you can pretend that this is ln a times x, that's what it is. So we have like ln a to the front, it's to the back, but it doesn't really matter, times x to the first power. I can write one exponent there. So we'll have 1 times ln a times x to the 1 minus 1, which is 0. So that's gonna, everything kind of just cancels out, and it really gives you just ln a. And e to the x ln a, we said was the same thing as this, same thing as that, and just a to the x. So we can actually just rewrite this as a to the x. So hopefully that kind of makes sense how I got this. And that's what I have here. Oh wait, oh I'm sorry, I wrote e. I meant to write a. Yeah, okay, so that's an a. And so yeah, that's basically how we got our formula. Okay, so how about this one down here? Well, that's also kind of a little bit similar. Here, let me just get rid of that. Okay, let me also get rid of this and this up top here so that we can have a clean slate. Okay, so this is also kind of similar because you can write, log base a of x as just the derivative of ln x over ln a. Right, that's just log change the base formula, which I have a video proving that. And so then we can write this as derivative of 1 over ln a, because ln a is just a constant. I think I didn't mention that earlier. Ln of a number is just a number, it's a constant, so it's not the same as this. This is just a number, this is a function. So basically the way we can work with this is say, alright, well, derivative of ln x is 1 over x, and we keep whatever's here. So we have 1 over ln a times 1 over x, which is just 1 over x times ln of a. And so that's this formula here. Okay, that was a lot, okay? We still have 2 more rules left to go, and then plus all the trigonometric stuff, which, yeah, who actually likes trigonometry, but it's okay, we'll get through it. Okay, so we have the product rule and the quotient rule, so let's just do one at a time, and then we'll combine both, and boom. So let's say we have the derivative. Alright, and I want to take the derivative of, let's do this, let's say 10x cubed plus, okay, so this is not a product, this is just a plus, and then I'll say x squared ln x. Right, so we want to take this derivative. So the way we can do it, so we can do each part. So whenever you have a plus, this is the same thing as the derivative of this plus the derivative of that. That's the beauty of derivatives. Now it doesn't work for like multiplication and division, it only works for addition or subtraction if you had it there. So this, we can say, well, the derivative of this is what? You hop this to the front, multiply by whatever's there, subtract 1. So this is going to be 3 times 10, which is 30, and then times x, and then we're going to minus 1, so it's squared. Okay, so now we have plus x squared ln x. This is multiplication. I can put a dot there for emphasis, where we need to use our derivative formula here. So this is interesting. So we take derivative of 2 functions, f and g. We take the derivative of the first, multiply it by just the second without anything, plus the derivative of the second times the first. So let's see that. Okay, so f prime, derivative of the first, is 2x, and then we just copy paste our second function, which is ln x. Right, that's just explicitly what it is, times g prime of x, or plus g prime of x, which derivative of ln x is 1 over x, multiplied by f, like our first function, which is x squared. Okay, so then this entire derivative is 30x squared plus 2x ln x plus x squared over x is just x. And so you can rearrange it the way you want. You can group these two together, whatever you want. And just note that this doesn't work at x equals 0, because, you know, you had that division there and it kind of messes things up. Okay, so that's our derivative. Now what if we had a quotient? What if we were taking, what if we were dividing in our derivative? So let's say our derivative was, we can utilize the chain rule here. We'll say ln of 5x squared plus 2 divided by, let's just choose one of these. We can say that this is going to be 3x plus, actually let's do e to the x here, e to the 2x, you know, just to make it a little, spice it up a little bit. So we're going to take the derivative of this whole thing. So from our formulae down here, yeah, I don't want to use the quotient and the chain rule. Actually, yeah, we can. We can say x e to the 2x. I'm sorry, but hey, you know. So we're going to use the quotient rule here. So the way I like to remember this, actually, so the product rule is pretty easy to remember. It's just first times the derivative of second plus second times the derivative of first, or the other way around, you know. It's pretty easy to remember. It's like one of each, you know. Here, I remember this as low d high minus high d low over low squared, okay? So low d high minus high d low over low squared, or low if you want. That's just an easy way to remember it. That's how I always remember it, so yeah. Okay, well, let's just start. So we're going to take g, which is just our bottom function, so we're just going to explicitly write it here, 3x plus x e to the 2x, right? Actually, and then multiplied by the derivative of the top, which is going to be, actually, I'm not going to have enough space here, so it's going to be a little weird, but so we're going to take the derivative of the top, which is the derivative of the top here. So this is going to be, we're going to treat this 5x squared plus 2 as its own little entity. So we're going to say it's the natural, so derivative of the natural log is 1 over x, so it's going to be 1 over 5x squared plus 2, okay, times the derivative of the inside, which is just going to be 10x plus 0, because the 2 kind of goes away, so this is going to be times 10x, okay, and then we're going to minus, okay, so I'm not done with this row yet, we still have to do the second part. The first function, which is just ln x plus ln of 5x squared plus 2, so, you know, we just kind of copy paste it here, and then we multiply it by our g prime. So this is going to be, yeah, so am I going to have enough space? Yeah, I will. So the derivative of this bottom is going to be 3, right, plus, so again, really easy there. This is where it gets a little complicated, because now we're using our product rule again. So we can say derivative of the first, which is just 1, that's pretty easy, and we leave this other one here, e to the 2x, plus, and now we take the derivative of e to the 2x. Actually, let me first take the, let me just first write x here, right, because that's our first function, and now we can take the derivative of this, so that's going to be e to the 2x, because derivative of e to the x is itself, which is a really cool thing, so e to the 2x, but multiplied by the derivative of the inside, which is 2x. Derivative of 2x is just 2, so we can actually just put a 2, so we can say 2x, so plus 2x e to the 2x. Okay, and then this whole thing is going to be divided by g squared, which is just this. We can just copy paste it, 3x plus x e to the 2x, square that, and boom. This is huge. This is such a large formula, but I wanted to have something extravagant for you guys at the very end, okay? These are not all of our formulas, but these are all of the examples I'm going to go through. The other ones I'm just going to give to you, and I think I'll make a video about them in the future. But as I said, I have a video about this, and this. And these two I kind of just proved to you for a little bit. Okay, so I'm going to show you all the sine formulas, and I'm sorry, the trig formulas, and then that'll be the end of the video, okay? Alright, so here are the trig formulas. Here, let me step out of the way. So you have the functions and the derivatives. So here are the normal trig functions, your normal 6, and here are their inverses. So here, derivative of sine x is cosine, cosine is negative sine, tangent is secant squared, cotangent is negative cosecant squared, secant is secant tangent, cosecant is negative cosecant cotangent, sine, and here are the inverses. Inverse sine is 1 over 1 minus x squared, inverse cosine is negative 1 over 1 minus x, the square root of 1 minus x squared, This is also square root, by the way. Inverse tangent is 1 over 1 plus x squared. Inverse cotangent is negative 1 over 1 plus x squared. Inverse secant is 1 over absolute value of x multiplied by x square root of x squared minus 1. And then inverse cosecant is negative 1 over absolute value of x multiplied by square root of x squared minus 1. So yeah, it's a lot of formulas, and definitely you have to remember these. I will definitely make a video in the future about these, and probably a separate video about these, just talking about them, how to derive them. And the last thing I want to leave you guys off with is some challenge problems. And I want you to find f prime of x, and just find the derivative, don't do any simplifications, and then I will give you the answers at the end. So yeah, that's pretty much it. So thanks for watching, and I will see you later. Bye guys.